But for the number two can provide another different kind of PO flow. Front and back. Number three go to the front and back. Do we have the three atoms connected next to each other? Yes. Right? Do we have the three PO because parallel each other? No, we don't. Okay? The first one, second one, they are empty. But second one and the third one, that is the different system. So far, so good. So you can see that the third one, first one is perpendicular, one is a front and back. No, not a conjugation, not conjugated system here. Okay? So that is the main point I want to discuss in the first page. But let's jump into the second page, and then based on the number in the second page, you can study the first page. Okay? So let's take a look at the second page here. So second page is let us know why benzene is stable. Okay? Let's take a look at the benzene. Instead of a 3 double bond over there, let's only focus on 1 pi bond there. Okay? We got 6 member ring, only 1 pi bond. But I want to convert that pi bond to single bond. I don't want pi bond anymore, so that's the reason I did hydrogenation. I added 2 hydrogens on those 2 carbons, So from double bond to single bond, I added 2 hydrogens. Hydrogenation. Okay? So and then I found, energy is released 28.6. So which means, the one with double bond energy is high. The one without double bond, that's the product. Cyclohexane over there, energy is low. From the one with double bond to the one without double bond, the process is exothermic. Energy is released 28.6. So write a picture over there. Probably that will be more. It will be clear. Okay, write a picture there. From double bond to single bond. So transformation is exothermic, right? How much heat is released? Okay, 28.6. That is the amount of energy released. Okay, 28.6. From double bond to no double bond. 6 member ring. Okay? And then now, I got 2 double bonds. So I want to convert those 2 double bonds to single bond. So that means the double bond on the right is going to release the energy 28.6. The double bond on the left, doing the same thing, is going to release the energy 28.6. So how much energy released in total? 28.6 from the right, 28.6 from the left. So in total, in order to convert this guy to no double bond, the 6 member ring cyclohexane over there, I need to do hydrogenation twice. Hydrogenation on the right, hydrogenation on the left, 28.6 released, 28.6 released. Together, that's how I got the number 57.2. 57.2. So far, so good. Okay, expected, and the experimental results matches up pretty closely. How about this guy here? We got 2 double bonds as well, but now it's adjacent, right? Okay, I have totally no idea about conjugation, so don't worry about conjugation. But when I did the expectation, the calculation here, I know this double bond on the left hand side is going to release the 28.6. This double bond will do the same. It's going to release the 28.6. So the same thing, 28.6 times 2, that is the energy we expected to be released. So 28.2 times 28.6 times 2, 57.2. 57.2, I put it over there. Exactly the same number. That is predicted. Okay? That's predicted. But then I did the experiment. I found, energy is supposed to release that much. But now, energy released less. So we only released the 54.9. Okay? Supposed to release the more energy. But now, energy is released fewer. Are we okay here? So that means, the molecule is more stable than what we expected. That is the actual. Okay? The actual only released the energy, 56.9, 54.9, but what we expected is 57.6. Is that good? So that's what we expected. Okay, that will be the amount of energy released, but the molecule only released such an energy, 84.9. Okay, it's more stable than what we expected. So what is the energy difference? 2.3. 2.3. Okay? Because of conjugation. Because of conjugation. We got carbon 1, carbon 2, carbon 3, carbon 4, boom, 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 boom. We got 4 carbons is on the same plane. Okay? They can talk to each other. So that's how the molecule can be stabilized by conjugation. We give the name to such kind of energy. We call such kind of energy stabilizing the molecule is the resonance energy. Okay? Resonance energy. So far so good, guys? So one pair, double bond, one pair of the double bonds can stabilize the molecule by 2.3. I'm talking about only, okay? I'm talking about only the resonance energy by conjugation. Resonance energy by conjugation. That is the amount of energy which can stabilize the molecule. Okay? Benzene. Benzene ring is over there. How many double bonds do we have? We got 3 double bonds, right? How many pairs of the double bonds can do the conjugation? How many pairs? How many? We got the pair, the double bond on the left hand side to the bottom right. That's the one pair. Is that right? We can have a conjugation there. The bottom right and the top right, that's the second pair. Am I correct? So the bottom right and the top right, second pair. Top right to the left, that's the third pair. So far so good. So I put those pairs of the conjugation in my mind. Okay? Let's do prediction. The prediction. So without any stabilization considered, and then I use 28.6. Each double bond. Each double bond going to release 28.6. So 28.6, 28.6, 28.6. So 28.6 times 3. So the whole piece supposed to release 85.8. 85.8. I put there. So far so good. Without consideration of any of the energy to stabilize the molecule. Without consideration of the conjugation. I don't worry about conjugation. I'll worry about conjugation later. Okay? And then how about experimental results? Here we go, 49.3. 49.3. So we're supposed to release 85.8. 85.8. That is the benzene. That is the predicted energy released. But now we only release, the molecule only released the 49.3. What is the difference? The difference is 36.5. 36.5. So benzene is way more stable than what we expected. So that is the energy stabilized. Okay? So the molecule is stabilized by such kind of energy. So we only release around 50. You do the subtraction, that is the energy. By such kind of energy, the molecule can be stabilized. Okay? And then we did analyze. Okay? What kind of a mechanism in the molecule can contribute to the stabilization of the benzene ring? And then, first of all, we know that we have the 3 pairs of conjugation, right? 3 pairs of conjugation. So conjugation 1, conjugation 2, conjugation from the top right to the left. We got 3 pairs of conjugation. Each pair of conjugation is going to contribute stability by 2.3. 2.3. So far so good? So based on the second experiment or third experiment here, we have the conjugation stabilization by 2.3 kcal per mole. If you have 1 pair, the molecule can be stabilized by 2.3 kcal per mole. Okay? Now we got 3 pairs. So 3 pair times 2.3, 3 pair times 2.3. So that is the energy provided by conjugation. Only 6.9, 7 kcal per mole. That is the energy stabilized by conjugation. Okay? What else? The molecule is stabilized by 36.5, but conjugation only contributes 6.9. So where is the rest of the 30? So 36.5 minus 6.9, so it's around 30. Where are those 30, remaining 30? So the 30 is the aromaticity. Are we good here? So aromaticity is one kind of mechanism to make the benzene ring. more stabilized than what we expect. Are we okay? That's based on experimental. And then later on, we are going to use a molecular orbital to prove that what is the aromaticity, how aromaticity can stabilize the molecule. Okay? So that is 29.6. That's what I mean 30 kilocalorie lower by such kind of energy. So aromaticity can stabilize the molecule. Okay? So that is the analysis on the page. That's a cyclized benzene ring or cyclized cis-member ring. You can do exactly the same analysis here as for the double bond to calculate what is the conjugation, the contribution by the conjugation over there. Okay, so I'm going to skip the page 1 over there. Okay, page 1, page 2 important? No, not important. But most important thing we have to know what is the aromaticity, what is the huge impact of the aromaticity to stabilize the molecule. Okay? In exam, in quiz, meter 1, quiz 1, quiz 2, there's no calculation. I'm not going to ask you guys to do a calculation page 1, page 2. Are we good here? Good? Okay. So focal point is not page 1, page 2, but I hope you guys can just based on those numbers can understand. Aromaticity is such kind of thing. That should be good enough. Okay. Now is the thing. This is important. Okay? This is important. So, under what kind of circumstances we can have the molecule, aromatic molecule? Okay? How we can find this molecule is aromatic, this molecule is not aromatic, this molecule is anti or anti-aromatic. It's against aromaticity. So we follow Huckel's rule. Okay? Huckel's rule. So you have to know what is the Huckel's rule. So there are 4 requirements. First of all, the molecule needs to be closed system. Okay? You need to have the ring. You need to have the ring. All atoms need to be connected. So far, so good. Okay. So for example, we know benzene is aromatic, right? So benzene is aromatic. Okay. Then how about the molecule? This one here. So we connect all the 6 carbons together. That is a ring. Okay? So how about this one here? CH3. CH3. We got xylene over there. Do we have all atoms connected? No, we don't. But we only focus on the closest system. We only focus on those 6 atoms. We don't worry about CH3. We don't worry about CH3. Okay? When we discuss the molecule is aromatic or not, then we only focus on the closest system there. So far, so good? Good. Okay. And then the second one here. Oh, do we have a conjugation? We need to have everything, all the atoms, fully conjugated. Okay? Fully is the key words. We need to have the molecule. We know, I think we know conjugation, right? But we need to have the molecule fully conjugated. Are we okay here? So for example, this molecule here. We have a ring, but do we have fully conjugation there? We don't, right? So carbon 1, carbon 2, carbon 3, carbon 4, they can play each other. We do have a conjugation between 1, 2, 3, 4. But 5 and 6 left out. 5 and 6 is lonely over there. Are we good here? So it's not fully conjugation. The molecule, sorry, is not aromatic. It's not aromatic. This molecule is not aromatic. Okay? It's not aromatic. Okay? And then the third one, the molecule needs to be flat. Okay? So the first one needs to be a ring. The second requirement, we need to have a conjugation, fully conjugated. Okay? And then the third one needs to be flat. They are 2 molecules I will ask you guys to memorize. Those 2 molecules will be tested in the meter 1. Those 2 molecules are not flat. All other molecules you can assume everything except for those 2. Okay? Is flat. Except for those 2 molecules. I will discuss those 2 molecules. Okay, now, number for pi electrons. Hey, how many pi electrons in the benzene ring over there? How many pi electrons? Quick. We got 6, right? We got 6 pi electrons. 6 pi electrons. Okay? So if you have a number among the pi electrons, if you have 2, if you have 6, if you have 10 pi electrons, 14 pi electrons in the system, then we consider that to fulfill one of the requirements for aromaticity, for aromatic. Okay? So if you use those numbers, convert it to the math expression. So 2 is the number, it's okay. 2 pi electrons, 6 pi electrons, 10 pi electrons, 6 pi electrons, that's a benzene, right? That's a benzene. We got the 6 pi electrons. Let me give you example 2 pi electrons. So this guy here. How many pi electrons over there? Hello, hello? How many pi electrons within the 3-member ring? How many? How many? 2. Is it a ring? Is this a ring? Fully conjugated? Fully conjugated? Fully conjugated? No, right? We only have one double bond. There's no third party joining, correct? sp2, sp2, and sp3. They have a p orbital. She has a p orbital. She has a bank. Checking account. He has a checking account. I don't have a checking account. Are we good here? So this guy here, this one there is CH2. That guy did not join the other 2 carbons. Are we okay here? Good? But now, I got hydrogen here. I got hydrogen over there. Okay? And then the other hydrogen pull away. I have partial charge there. Partial charge over there. Do we have the 3 p orbitals connected? Do we have the 3 p orbitals connected? Hello, hello? Do we have the 3 p orbitals connected? Yes, right? And then they are parallel each other. Okay? They are parallel each other. So is that okay, guys? Good? So you have 3-member ring, only 1 double bond, 1 of the carbon is partly charged. Okay? So that partly charge can jump around. The partly charge can go to the carbon number 2, carbon number 3. So far, right now, it's at carbon number 1. Are we okay here, guys? Good? How many pi electrons? How many pi electrons? 2. We only have 2 pi electrons. 2 pi electrons. So the first one, it is a ring. Yes, it is a ring. The second one, fully conjugation. Yes, that's a fully conjugation. 3 p orbitals parallel each other. Carbon 1, carbon 2, carbon 3. 3 p orbitals parallel each other. Okay? Carbon 2. So this bond is in front of us. Okay? The bond 1, 3 is at the back. Okay, at the back. And number 3. Is the molecule flat? Yes, molecule is flat. And then number 4, how many pi electrons? We got 2 pi electrons. Okay? If you fulfill 2 pi electrons, the next one plus 4, 6 pi electrons. So 2, 6, 10, 14, 18, and so on. Then we'll fulfill one of the requirements for aromaticity. Then we use the math expression. Then that will be 4n plus 2 pi electrons, right? N can be 0. When n is 0, we got 2 pi electrons. When n is 1, we got 6 pi electrons. That's benzene. That's a benzene. So far, so okay, guys? Good? Okay. So this one is aromatic. Aromatic. So this one is aromatic. Okay, let's go back. Okay, here we go. So number 4, okay, we need to have a 4n plus 2 pi electrons. N can be 0, N can be 1. You can have starting from 2 electrons, the next one will be 6 electrons, 10 electrons, and so on. Okay? Okay, so that's the Huckel's rule. So let's analyze those molecules on top. Okay? So, how about the first one? Do we have a ring system here? Hello guys? 4-member system, 4-member ring. Yeah, this is the ring, right? This is the ring, correct?
Yes.
This ring, correct? So far so good. Okay, how about conjugation? So double bond can go nowhere. So we do have a conjugation there. We got conjugation there. Check mark. And then, oh, this one, checked. Okay? How about this guy here? Let's discuss that one later. Okay? Let's discuss this one later. How about, let's talk about flat. The molecule is a flat or not. So we got 4 carbons, then that's one is flat. We got 6 carbons, benzene, we know that's a flat. But 8 carbons, no, this one is not flat. It's not flat. So the molecule is like this one. Okay, so you can see that 2 sides of the carbon-carbon just popping out. It's not on the same plane. So that's a Ca. H8. We call this one is 8. Annually. A-N-N-U L E-N-E. A-N-N-U L E-N-E. So far so good. That is one of the example. One of the exceptions. We have 2. That's why it's 1. It's not flat. Okay, it's not flat. In the exam, I'm not going to share with you which one is flat, which one is not flat. This one is not flat. You have to know. The other one you have to know. And then we have the common language. Right? All others you can assume they are flat. Okay? If that is a non-flat, I'll mention that in the exam. Okay? So this one is non-flat, then we don't have a free conjugation, right? You need to have the p-orbital, parallel, right? So those 3 carbons, 1, 2, they are parallel. 3, 4, they are parallel. Oh, that's 2 different types of the parallels. Are we doing here? We don't have the 3 p orbitals connected. We don't have the 3 p orbitals. All 3 p orbitals parallel each other. So sorry, no, not a conjugation. Not fully conjugated. Not fully conjugated. Okay, number 5 electrons. We got 4, we got 6, we got 8. Doesn't matter. The last one here. This one, we already have 1 out. Not qualified. So this one is non-aromatic. This one is non-aromatic. Benzene ring, aromatic. Okay? And then the first one here is tricky. The first one here, we fulfill all 3 the requirements, but we have 4 pi electrons. We say this one is N-pi. N-pi or N-T, aromatic. Okay? So this one, so benzene ring is more stable, right? What we expected. This one here is more stable than we expected. But N-pi, N-T, that's why it's less stable than what we expected. This one is less stable than what we expected. Okay? We know what is aromatic, but now, next page, let's know what is N-pi aromatic. Okay? I need to jump to the next one, N-pi aromaticity. Okay? So, the next one here. Here we go. This one here is the N-pi aromaticity. So, we need a ring, no problem. We need fully conjugation. Okay, let's write it down. Fully conjugation. So we need a fully conjugation. And then we need flat. We need flats. Those 3 are exactly the same as the first 3 in the previous page. So the first 3 in the previous page is here. It's a ring. It's a fully conjugation, and it's a flat, right? But only the number 4 different. So in the previous page, by Gauss rule, we need 4n plus 2. But now, we have a 4n pi electrons. 4n pi, which means, hey, how many pi electrons do you have? 4, the next one, plus another 4. The next one, plus the second 4. So we have 4 electrons, 8 electrons, 12 electrons, 16 electrons. So use the math expression, then that will be 4 times n, and it can be 1, 2, 3, 4. Okay? So we have 4 electrons, 8 electrons, 12 electrons, and so on. So far, so okay, guys. Good. Let's do more examples here. Okay, talk about it. So those 2 pages are important. That will be the first question on midterm 1. First question on midterm 1. 1, 9. Probably, I like to say probably 20 points. Okay, 20 points. I have my midterm 1, I have my midterm 1, previous midterm 1, previous midterm 1 P posted on cover. Those are pretty accurate. Okay, pretty good. Pretty, yeah. Represent, okay, what you are going to have actually. Good. I'm an old guy. I don't want to change. Okay? So, especially for students in my 25K, you know my style. Okay? If you want to ask from my 25K, ask around. Okay, what is my style? And then, I think I'm a pretty simple person. You work hard, you deserve points. You have an A from JChem 1, JChem 2. I don't FK. Do you hear, guys? Good? Okay? So students in here, I know her, I know him, I know him. Oh, you have to check email information. Oh, yeah, I remember you. You have a chess bank. Yeah, chess bank. Oh, yes. Sorry, guys. So try to sit in the front, okay? And try to go to office hours. Try to discuss with the TAs as well, okay? So we have a TA Chen Hao over there. So students probably don't have a recitation. TA Chen Hao. I worked with TA Chen Hao for probably two semesters already. And then actually Chen Hao was sitting in your position. Chen Hao was our undergraduate chemistry major, okay? And we have a TA. Adash. You can see that. I'm not quite familiar with his name, but he's first time working with Adash. Adash came with it. Yeah. And we have Yuxing over there. And then all 3 are PhD students, year 3, right? Yeah, year 3. Okay? So let's go back. So the first one here, the first molecule is a ring. Hello guys, is this guy a ring? No, it's not a ring, okay? The second one is a ring, third one, fourth one. No problem. Okay? It's no problem. How about conjugation? Oh yeah, first one conjugation, but it's not a ring, so we don't have to discuss that one anymore. Okay? No discussion. So this one is non-dramatic. Okay? Non-dramatic. Okay? How about the second one here? Do we have conjugation here? We have a nitrogen. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. They can talk to each other. That is the parity there. Are we good here, guys? Good? So we got conjugation there. Okay? No problem. How about the last one here? Oh, we discussed 3-member ring, right? The 3-member ring. But now I just changed it to 5-member ring, right? So carbon 1, carbon 2, carbon 3, 2, 3 can talk to each other. But the 1, 2, 3, 1 can talk to 2 and 3 because the number 1 has lone pair. That lone pair can be the PO orbital. Okay? This guy here, the 1 can be in the P orbital. I share with you guys, right? Here we go. That's the same system here. This one here, but I just changed this one too. No pair. Minus no pair. Okay? We can still have the P orbital on carbon 2, P orbital on carbon 3. So fully conjugation, ring system flat as well. Ring system, fully conjugation, flat. How many pi electrons we have? Quick, I'm hungry, quick. How many pi electrons we have? How many? 4 pi electrons. 4 pi electrons. Okay? So we got 2, that's between carbon 2, carbon 3, that's a double bond, right? So we got 2 pi electrons. But this one here can be donated to act as a pi electron to form a pi bond. So carbon number 1. So 2 plus 2, we got 4 pi electrons. 4 pi electrons. Hey, those 2 molecules has no relationship, okay? And then this molecule is a ring, fully conjugation, flat, 4 pi electrons. So this molecule is anti-L-1-T-4. So far so okay, good, guys? Okay. So let's go back to the current slide here. Okay, so this one is okay. We can use the p orbital to talk to the carbon 2, carbon 3. Okay. So this one here, yes, this one is the conjugation there. Okay. Flat, we don't have to worry about that, right? We don't have to worry about that. That's non-aromatic already. So how about molecule number 2? That one is flat. This one is a flat. This one is a flat as well, because that's not two exceptions. Okay? Those are not the 2 exceptions. So they are flat. How many pi electrons we have? So for the molecule here, we got nitrogen and 1. So nitrogen and carbon number 1, we got double bond there, right? We got 2 pi electrons. And then carbon 2, carbon 3, we got double bond. Carbon 4, carbon 5, we got pi electron over there. So we got 2, 2, 2. We got 6 pi electrons. Okay? So we have 6 pi electrons. How about molecule here? So this molecule. Oops. Double bond, hydrogen, minus. How many pi electrons there? 6 pi electrons. Are we good here, guys? Double bond, each one 2, 2 plus 2, 4. But we do have a lone pair, okay? Lone pair. That's lone pair can donate it into the system to make a pi bond. So we got the 6 pi electrons. 6 pi electrons. Okay, let's go back. Okay, so this molecule is exactly the same thing as this molecule here. Okay, that's the same molecule. 6 pi electrons. Okay, how about the last one? How many pi electrons? Hello? 4. 4 pi electrons. So we know this one here. Aromatic, no problem. The third one. Aromatic, no problem. The last one is anti-aromatic. Okay, anti-aromatic. Do it here. Okay, so hydrogen here, we got positive charge. This positive charge is in p orbital. You guys need to know that, okay? You guys need to know that. Okay, good. Okay, and then I don't have time to address that. I believe probably 40–50% of students know already. How about this lone pair here? This lone pair is in sp2 orbital. sp2 orbital. Okay? If you don't quite understand, ask around and then ask TA or discuss with me. Okay? sp2 orbital. Okay, good. We have more examples. So far, so okay, guys? Good. So now, let's talk about the neutral anilines. So in this page, the first target, let's focus on the keywords. The keywords is neutral. Okay? The keywords is neutral. Okay? I don't worry about aniline. I focus on the neutral. So we are talking about no charge system. There's no positive charge, there's no negative charge. Okay? So the first one here, we have a 4. We got 4 pi electrons. Okay, we got 4 membrane, 4 pi electrons, we got 2 double bond. And then benzene ring, we have the 6 pi electrons, 6 membrane. A membrane, we got 8 pi electrons. And then how about 10? 10 membrane. 1, 2, 3, 4, 5, 5 pi. 5 pi bonds. We got 10 pi electrons. We got 10 pi electrons. And then we have 12, we got 14, we got 16, and so on. Right? So that's the reason I use my knife to cut it, right? We got dash line. The dash line below dash line. We got 4N system here. So here, we have 4N pi electrons. 4, 8, 12, and then 16. How about above? Those we have a 4N plus 2. 4N plus 2. 4N plus 2. If we assume everything is flat, then those molecules above the dashed line, they are aromatic. Okay? They are aromatic. Everything is flat, those molecules are beneath the dashed line. Okay? So they are, oh, let me put here, or in here. Anti. They are anti-aromatic. Anti-aromatic. But as I mentioned, there are two molecules, not flat, not flat. One of them is this guy, it's the 8-annuline. Okay? 8-annuline. It's not aromatic because of it's not flat. It's not flat. Hey guys, in our class, I like to use a symbol. I don't have time to write so many words. So this is the because of. This is the because of. This is the therefore. Okay, that's the because of. That is the therefore. Are we still here? I think probably that's an old expression in math. Because of, therefore. Good here? Okay. The other one is 10-annually. 10-annually. Okay. So this one is the 10. We got brackets and then annually. A-N-N-U-L-E-N-E. That's the name. We got 8 annually and the 10 annually. Let's put the 8. N-N-U-L-E-N-E over there. 10 annually and the 8 annually there. So those two, okay guys? Provide this. So those are not flat. Those two are not flat. Okay? I'm talking about neutral one, okay? That is the exactly same molecule. If you have a exactly same structure and 8 membrane, 10 membrane, they are not flat. They are not flat. Okay. So now, okay, let's keep doing the following. How about that? Let's use this one homework. I will post the key to you guys. Is that okay? So I will post the key to you guys. And then just using the analysis we discussed about Huckel's rule for aromatic and anti-aromatic. Then you can do analysis by yourself. Good here? And then also analyze which orbital, and which orbital. Also analyze which orbital can afford the lone pair. Okay? Good? So in the meter one, I'll give you a structure. Based on structure, you have to be able to tell this molecule is anti-aromatic or non-aromatic. This molecule, how many pi electrons? So if I do have a lone pair, then where is that lone pair? Which orbital to support that lone pair? You have to be able to answer. Okay? So homework, I will post the key to you guys. So let's take a look at the application here. How we can apply aromaticity, anti-aromaticity into the chemical reaction here. Okay? So the molecule A, molecule B, now we got water over there. I want to do SN1 reaction. SN1 reaction. Hey, what is the first step? SN1. First step, SN1. Say that again. Bromine leaving, right? So we got bond cleavage. So bye-bye ER. So we have the molecule. We still have hydrogen there, right? Plus this one here. We got double bond. We got hydrogen. And the plus over there. So far so good. Have you seen something? So one of them is less stable than what we expected. Which one is less stable than what we expected? The first one, intermediate or second intermediate? The first cation or second cation? Yes. Second cation reason? What's the reason this one is less stable? Do we have a ring? Do we have a ring here? Do we have free conjugation? Is this one flat? Yes. And then how many pi electrons we have? 4 pi electrons over there. So this one is anti-aromatic. Okay? Anti-aromatic. anti-galvanic. So this one here is less stable. This one here is less stable. That means the intermediate energy level is higher, then activation energy is higher. We need to use provide, as a scientist, we need to provide a lot of the energy into the system in order to break the VR, in order to convince, hey, no problem, you can stay there. We can put the partial charge on carbon number 1. It's no problem, but we need to use a lot of energy to convince the molecule. Your molecule is highly, highly unstable. Good here? So that's the reason. Okay, that's stable. Activation energy high. Okay? The first one here. Activation energy is okay. And then we can make the OH attached after the two more steps. But this one here, because of those reasons, in general, no reaction. No reaction. So now you can see that we have to add aromaticity, anti-aromaticity into the SN1, SN2, E1, E2 reactions here. Okay? So that's the application here. Down the bottom here, we have another one. Let me use this one as a homework as well. But let me discuss how we should solve to analyze this question. So this one here, we are going to compare HA, HB, HC, which one is more acidic, right? I don't know, but I know how to compare the stability of the conjugate base. So let's get rid of hydrogen first. If I get rid of hydrogen, I have a minus over there. Good. Uh-oh, I found something. Here we go. The second one here, get rid of HB. Get rid of HB. Hydrogen there. I got conjugate base. Okay? Get rid of HA. I got minus over there. So conjugate base. Okay? And then if this one is A, this one is B, this one is C, we got A prime, B prime, C prime. Which one is more stable? The more stable the conjugate base, the stronger the corresponding acids, right? So which one is more stable? Blah, 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 blah. Which one? A prime, B prime, C prime. Which one is more stable? C prime. C prime is more stable than possibly expected. Okay? So we don't have to put a lot of energy in. We can get rid of HC easily. So this one is, it's a ring, it's a fully conjugation, it's a flat, we got the six pi electrons. 6 pi electrons. This one is galvanic. I tell you guys already, so let's write it down. Acidity.